Okay, assalamu alaikum wa rahmatullahi wa barakatuh. Let's begin the lecture. Of course, we're gonna go briefly on this because you know the lecture and the notes already on e-learning, but we're gonna go quickly on that. So as you recall, for the past 5 chapters, we've been talking about random variables. We analyze random variables, we understand it well, and today we're gonna introduce a new function. It's called the random processes. And the random process, basically the difference between the random variable and the random process is basically assigning a time function to every outcome according to some rules, okay, to every outcome in the random variable. And it's denoted by equation 2, as you can see here. If you compare equation 1 with equation 2, equation 1 is the random variable, and equation 2 is the same thing. The only difference is we are including a time function t. So that's basically the random process, okay? So as an example here, so we can understand the random process a little bit better. So if we have this experiment, which is tossing a dice, which we did that. So this example several times before during the random variables, when we talked about random variables. So obviously the outcome for this one is going to be 1, 2, 3, 4, 5, 6, because it has 6 faces. And this is the sample space for it is S. Okay, now if we assign a time function or a time for each outcome, so we have 6 outcomes, so we're going to end up with different, different time function for each one of them. So for example, when the outcome is 1, x1 of t, which is the random process here, it's equal -4. When the outcome is 2, it's -2, and so on and so forth, as you can see here on this table. I think it's obvious here. Now this set here, the set of functions from x1, x2, 3, 4, 5, 6, as you can see here, this set of function, it's called a random process, okay, as shown in equation 3. And this set is also called a family or collection or ensemble of time functions, okay? So in the book, you might see some books actually, they call it the family of time functions or a collection or ensemble. They all mean the same thing, okay? And each member of the time function, like for example, x1 of t or x2 of t, it's called a sample function or ensemble member or realization of the process. So we might say the realization of the process, which is it's a member of the whole set, one member of the whole set, okay? So this is the general definition in front of you, but we have a random process for discrete and for continuous. Now, for discrete random variable, it's going to be denoted by xn of s, because n is the discrete numbers, okay? And for continuous time random process, it's going to be xt of s, okay? Now the next thing we're going to talk about briefly, very briefly actually, it's we have 4 types of random processes, okay? And they all depend on whether the random variable and the time are continuous or discrete, okay? And we're not going to go through this in details, but this is just for your information. So we have 4 different types of random processes. Now, if both the random process and the time are continuous, and then we would call this random process continuous random processes, okay? If both of them are continuous, like this example here, both of them are continuous, okay? The x and the t, the y-axis, which is the random process, and the t, both of them are continuous, then this random process is called continuous random variable. So this is the first one. The second one, if the random variable is x, the random variable is discrete, but the time is continuous. Okay, if one of them, which is random variable, is discrete, but the time is continuous, we refer to this one as discrete random process. Discrete random process, which means the random process, the time we do have a random process, which is the time is continuous. Okay, but the random variable is discrete, so we call it discrete random variable. On the other hand, if the random variable is continuous, but the time is discrete, okay, then we call it continuous random sequence, continuous random sequence. And sometimes we call it a discrete time random process, okay? Continuous random sequence or a discrete time random process. In this case, the time is discrete, but the random variable is continuous. And the fourth type, obviously we have some examples here for you, for your reference. And the fourth one, if both of them are discrete, the random variable as well as the time function, both of them are discrete, then we refer to this random process as discrete random sequence, discrete random sequence. And we have this example right here, okay, for you. And then we have what we call deterministic and non-deterministic processes. Okay, what does that mean? The deterministic process is when you have a function and the behavior of the function, okay, the current behavior of the function, you can use this behavior or this information to predict the behavior of the future of the function. Okay, how, for example, if we have, let's say, if we have this sine wave function, okay, and this is for a full period, okay. Now, we know this is a full period of the sine wave. Now, by looking at this, we can tell the future, how this function going to behave in the future, because this is you know, this is you know, it's continuous, okay. It's and it's easy to deal with, okay. So we can tell that from this shape that the second period is going to be the same. It's going to be something like this, and the third period, and so on and so forth. By doing so, this function, it's called, or this process, is called deterministic process. This x of t here, a sine omega t plus theta, is a deterministic process. Why? Because we can tell from the information we have at hand, the current information we have at hand about the process, we can tell the future of the behavior of the process. Okay, so this is deterministic. On the other hand, if we have another function that it's unpredictable, as you can see here, it's, you know, it's كان عشوائي, okay, it's unpredictable, okay, so we can't really tell the next period whether it's going to be the same shape or a different shape. In this case, this process, it's called undeterministic or non-deterministic. Okay, so that's a difference between deterministic and non-deterministic. So we can deterministic, we can predict the future behavior of the function based on the current information you have at hand. On the other hand, if you have another function where it's unpredictable, it's you can't really predict. It changes. Okay, it's not consistent. Okay, you can't really tell how the next period is going to be, which means it's unpredictable. Okay. The next thing we're going to talk about something called independence and stationarity. Independence and stationarity. Now, as you can see here on the first page here, a random process become a random variable when time is fixed at some particular value. Well, that's given, because like we said, the difference between the random variable and the random process is the time, assigning the time to each outcome. Now, if the time is fixed, obviously it's no longer a random process. It's just a random variable, okay? Now, a random process is said to be stationary if all its statistical properties, and we did talk about these properties in the past, in past features like means, moments, variance, covariance, and things like that, that are related to its PDF. Of course, we use the PDF to get these properties for the random variable or the random static. Do not change with time. So if they do not change with time, it means this random process is stationary, which means like it's a random variable, okay? Now, if it does change with time, it means if it's obviously is non-stationary random process, okay? Now, before we do that, before we continue talking about independence and stationarity, let's just introduce the CDF and the PDF for the random process. And by the way, it's very similar, or it's the same function as we had for the random variable. The only difference is we're going to include the time function in it. For example, equation 1 right here, this is the CDF for the random variable, if you remember. Okay, now the CDF for the random process, x of t, we're just going to use x and t here. We're going to include t. So it's going to be x of t. X of t, this is the random process less or equal to a specific function of x. Okay. And of course, if we have more than one, then we're going to include it as shown here, like joint distribution function is going to be very similar to, or it's going to be equation 3, as you can see here. The fx of x1, x2, t1, t2 is going to be the probability of the random process x t1 less or equal to x1 and x to t2. This is the joint CDF for the random process. And similarly, like we did in the past when we dealt with the random variable, we can extend that to several, nth order of joint distribution, okay? Now, as far as the PDF, how are we going to get the PDF? Very similar, the similar way we used for to find the PDF from the CDF for a random variable. We just take the first derivative of the CDF. So the same thing here, as shown in equation 5, we take the random variable, the first derivative of the CDF for the random process with respect to t, and that will give us the PDF for the random process for that particular random process. And also, if we have multiple ones, we will take, of course, this is a partial derivative, okay? You will take the CDF, if we have joint CDF. You will take the first derivative with respect to x, and then the outcome, you will take another derivative with respect to x2. And this is just a quick introduction about the PDF and CDF, because this is, and as you can see, there's no difference between these shapes or equations and the previous equation. The only difference is t is included in this equation, okay, the time. Now, statistical independence. Of course, we did talk about independence several times. We did talk about it in chapter 2, maybe, or 3, and also we talked about it in chapter 5, and we understand it very well. Okay, as it says here, two processes, x of t and y of t, two random processes, x of t and y of t, are said to be statistically independent if the random variable group, okay, which is x1, x2, xn, all of these are independent of the other random variable groups for y. So the random variable groups for x is x1, x2, x3, and so on, as shown in equation 7. And the random variable group for y of t is given in equation 8, okay? So if these two equations or two functions or groups are independent of each other, then we can say that these two processes are independent of each other. And also says independence requires that the joint density be factorable by groups, which means that if we have a joint PDF of x and y, it can be written as shown in equation 2. Like if we have x and y, if you remember when we talked about random variable, if x and y are independent, we can say that the joint PDF of x and y is going to be the marginal PDF of x times the marginal PDF of y. And that's exactly what we're saying here. So that's what we mean by factorable by groups. The first thing we're going to talk about in this chapter, or one of the properties, is the mean. And the mean, it's given in equation 11. And if you go back, let's say to equation 3 or equation, to chapter 3 or chapter 5, it's exactly the same equation, okay? And the mean of the random process x of t is given by the expected value of x of t, where this one here is the PDF of the random process, where in the past we said that this is the PDF of the random variable. So if you understand the mean in the past, that's nothing new to you, okay? All you have to do, just replace, if you have the PDF, just plug it in here and you will find the mean for this one. So this is the first property of the random process. So this is just a simple example. It says here, given random process x of t, it's equal a sine omega naught t, okay? Where a is a random variable uniformly distributed over 0 and 1. So in this case, in this random process, a is the random variable, okay? Not sine omega naught t, which means sine omega naught t it's not going to be included in the calculation here, right? So which means we need to find the PDF for a, okay? And if you go back to chapter 3 or chapter 2, when we talked about uniform random variable, okay? This is just so this information, just to refresh your memory. You can find the PDF for a in this case is 1 over b minus a, where in this case b is 1 and a is equal 1. So the PDF of a in this case is going to be 1 right here, okay? So now we just do the integration from 0 to 1. Sine omega naught t is going to be out because it's not included, since a is the random variable. It's not sine omega t, okay? And obviously do the integration, and this is a very simple integration. And you will end up with this this result. So the mean for this random variable, it's half sine omega naught t, half sine omega naught t. And of course, if you recall, this is the mean. This is when we talked about this uniform random variable in chapter 2, I believe. We introduced that in chapter 2. We said the mean for a random variable for a uniform distribution, it's going to be a plus b divided by 2. A plus b divided by 2. So really, without doing all this integration, you can just plug in 1 over sine here, which is this is the value of this integration. So either way, it's fine. And that's all I have for today. On Tuesday, inshallah, we'll continue with chapter 6, where we're going to talk about some more properties. Today we just talked about the mean. Next time we're going to talk about some other properties related to the new function, which is the random process. Any question related to today's notes?
دكتور
تفضل.
بس بالنسبة للسؤال الغلط اللي كان بالمد ما راح تقدر تصحح لنا علامته ولا كيف؟
بعد ما طلعتش عليه، بس اذا لكم علامه بعد ما نزلتش العلامات الصحيحه، لان بتعرف هاي فتره تكون الامتحانات. بس اذا لكم علامه ان شاء الله بتاخذوها بعد ما نزلتش العلامات. ما نزلتهم ما نزلتهم؟
لا تمام.
اوكي ان شاء الله اذا لكم بتاخذوا ان شاء الله. توكل على الله. Any other question related to the notes or anything else? Okay. Then if you didn't have any questions or anything like that, ان شاء الله بنشوفكم ونحكي